speaker. He's shaking his head. He's like, no, you're not. No.
Liar.
He's a new face to the cloud village, but a veteran speaker. He's spoken at BSidesSF, Melbourne, Canberra, and more places.
Canberra.
I apologize to all the Australians who just cringed listening to me try and say that. Sam Stewart, who goes by Frenchie, is a CEO and founder of Ensignia Security, and previously InfraSec at Brex, Cruise, and Culture Amp. Frenchie will be introducing Runtime Reachability. It's a novel approach that leverages continuous profiling via eBPF to quantify how often a vulnerable method or code path is called in actual production usage. The name of Frenchie's talk is Runtime Reachability, prioritizing vulnerabilities with eBPF and continuous profiling. Please give a warm welcome to my favorite Australian, Frenchie.
Thank you very much, Mike. Can I get a mic check? Hey, it's Mike. Sorry, I do that every time I present with Mike. Mike and I are dear friends. Somehow he keeps letting me goof around on stage. Thank you so much for coming in. This is kind of a bit of a mad ramble. I really just want your feedback. That's the main thing. Yeah, as Mike already gave the introduction, I speak and ramble on cloud, clusters, containers. Anything starting with a C generally is what's interesting to me. Bit of an overview of what we'll run through, the problem statement that I'm trying to solve for with this, because I think that's worth being precise about, and then a couple of background things. There'll be a lot of prior research, so if you're not familiar with continuous profiling or eBPF or any of that stuff, that's great. We'll hopefully bring you up to speed. So that's surprisingly low resolution. I'm hoping that that's not an indication of the Wi-Fi. So this is an image of going the wrong way through traffic, right? So part of this, for me, is I don't think I've heard of anyone else taking a similar approach with this. I think it's novel. If anyone has heard of a previous thing, please tell me, because if I'm just an idiot and I'm going the wrong way through traffic, let me know. But I think this may also be a really useful way of how we can actually quantify the likelihood of vulnerabilities. Because I think at the moment everyone kind of agrees that vulnerability management is broken in its current state, right? So software composition analysis is useful. It's an important part of building software securely. However, the volume of crap that we get out of these, right, is just, it's ridiculous. Everyone's seen something that looks like this on incredibly low resolution. This is amazing. Let me see if the PDF has finished downloading. What's that? Oh, it literally got better. I also may have a downloaded PDF, which I'm going to try and see if I can switch to that. 1 minute left. All right. I'll keep running with this before switching over. But if it continues to suck, then my sincere apologies. And we'll switch to the offline version when it's done halfway. Cool, so everyone's probably seen something like this, right? So, 30,000 critical vulnerability, 300 and something. This is a meaningless number, right? And this is from a mid-sized organization. You all probably have seen something similar to this. It's not even necessarily indicative of the actual risk that the thing presents. It's just, hey, all this SEA, they're all criticals, everything's on fire, everything's high. So your choice of meme, you can either pick, the number of vulnerabilities is way too damn high, or over 9,000, depending on your different vintage of memes. And typically in a dashboard, this is a mock-up of something. You probably have a system like this, your task management thing, everything's red, it's over 9,000, and you're just wrestling to try and figure out which ones to actually patch first. And the reality is, as security practitioners, we're all really short on time. We don't have the ability to go through and fix absolutely everything. We'd love to with infinite resources, but there's a judgment call that has to be made as to which ones actually matter to fix, right? So there's a couple of things we'll go into around how we can actually go about this, right? But as an industry, we've kind of just looked at likelihood and shrugged, right? Impact is the criticality of the vulnerability, sure, but likelihood, is it publicly accessible? Maybe, it depends on the context of the business, shrug, right? We don't have an answer. What if we actually had a scientific method of actually calculating that likelihood? Could be interesting. Maybe that's foreshadowing. So a couple of background things. So continuous profiling is, I won't read the words off the slides, but it's a method by which we can analyze the performance of applications. In our context, we really care about CPU. That's really the only thing. But by background, what is profiling? I'm going to give this a second to see if that comes online. But the image itself isn't too specific. Basically, it's just all of the different things within the Linux perf events. You can check out disk events, you can check out network, you can check out a whole bunch of things. CPU is the one that we care about in this particular context. And there is a whole book on BPF performance tools. If you want to go deep into actual performance, that's background reading.
Great book.
It's a great book? Yes, indeed it is. Yeah, very chunky. But you don't need to go into that far detailed into actually understanding it. It's a good book, but really for this context, we only care about CPU. There's a command like this, perf, record particular events. It samples on a regular basis and will tell you different things, right? So you can give it a specific command, a process that's already running, and it will dump out onto disk some performance information. In this case, this is a file I/O structure, but it dumps out some stuff like this. Another image. All right, I'm gonna give up on this and switch to slides. Hey, okay. And just full screen this. Sorry, I appreciate you dealing with this on the fly. Hold on, I will do this and this. And cool. All right. Jump back to here. Cool. All right. Hopefully you can see that a bit, and I will share these slides afterwards as well, so you can see it. But in the case of CPU, it'll dump out an entire call stack, which looks something like this, which is pretty ugly in and of itself. But whenever you get that wall of text, whenever your error comes out, it's like, something's broken, you see the entire call stack, the path of which code's taken. It represents something like this, which is relevant in this context in terms of vulnerabilities, which we'll get to in a little bit, because we want to know which vulnerable code path is of interest to us. There's a great visualization tool called Flame Graphs, this is also a bit of background knowledge that you need to know. Brendan Gregg has done a bunch of great work around this, but they look like this. At first glance, they're pretty ugly, but they contain a lot of information and they're really useful. So basically, if you imagine the process tree, the tiny little tip at the very top, that's just profiled and seen less frequently than something that's all the way down the bottom. So you can infer the number of times a second that it gets sampled, that shows up more of the time. Now this is useful in performance monitoring applications. If you want to know, hey, what's taking a really long time in my application, right? Is it a database query? Is it a network call? Something's running slow, I don't know what. I'm going to look at the flame graph and figure out what actually goes on. So that's useful background information there. So we just do that continuously, bingo, right? And then that's continuous monitoring, right? Well, it's a little more complicated than that. Unfortunately, that can tank performance and grind things to a complete halt. It's useful data, but typically if you do that on everything, well then you don't need the flame graph because things will run slow. You just know that. Enter Google-wide profiling, so this is 2010. One of the key features of GWP was that they were able to do this with negligible overhead. Negligible? That word, thank you, yes. I can usually get away with saying funky pronunciations as just an Australianism, but there's Australians in the audience, so I can't do that this time. But the useful thing here is, sampling-based techniques, and so they do this in a non-invasive way. Very interesting foundational paper, would recommend reading that as well. The data structure that Google now supports is one called pprof, right? So there was the perf.data events, there's now also pprofs, which is a protobuf. So it's a more efficient data format as well. This is a useful tool that's worth checking out if you're getting into profiling. And then to convert in between the two, these are some of the other useful tools that I've come across over time. Here's a bit of a history lesson. So yeah, that 2010 case. Now there's a few other players out in the market. This is from the CNCF. The one we'll talk about specifically is Parker. It's an open source tool from Polar Signals. But there's a bit of a history lesson. A few other people, Pyroscope's out there, New Relic and Amazon, they all have their different variants. But all of these tooling now give you the ability to do that performance monitoring in a continual basis. This is well known within the observability world. For the security world, still kind of new as far as I'm aware, unless there's some SREs and sysadmins in here. But we'll drill into Polar Signals specifically. Worth giving a shout out to OTel as well. So OTel's an open standard for this. Elastic just released some tooling that does a lot of the similar stuff that we were doing internally, and then they released a tool months after we were already doing it. So it would have been great to have that at the start, but OTel as a new standard for multi-language support around this stuff as well, which is cool. And the way specifically that polar signals works is via something called eBPF. So a bit of background if you're not familiar. They are small little applications that are compiled and run within kernel space. So again, coming back to that performance consideration, when perf was prohibitively expensive, eBPF is an enabling technology that lets us run these within the kernel itself for a bunch of different applications, right? So you can check out networking calls in a high-performant way. You can do security things. So, for example, intrusion detection systems or malware. You can have some highly performant ways to monitor that sort of stuff. There's a bunch of tools there on the slide. To be specifically clear, though, we are not interested in the security use case of eBPF for this talk. That is not a guarantee. It is the observability side. And I'll go into reasons why later. But you don't actually need to be writing your own eBPF programs for this stuff. The Parker, the tooling, if you want to, you're more than welcome to. But if you just want to take the tool and run it off the shelf, that's also fine too. But yeah, if you want to go and learn on the eBPF, it's really cool stuff. Functionally, why is it performant? So this is the user space and kernel space kind of boundary. There is a high volume, that ring buffer. In this case, it's sysdig because that's their documentation. But yeah, you can see the eBPF program running within the kernel boundary itself, and there is a tight loop around that. Low volume data bouncing back and forth. More detail than that, you don't need to jump into so much detail, into detail for this talk. Parker is the specific tool that I mentioned. It allows for continuous profiling via eBPF. The reason why that is interesting, as I mentioned, is performance. And in our case, we really just care about CPU. It also has broad language support, which is pretty handy. So a bunch of ahead of time, so things that are compiled, C, C++, Go, and so on. Just in time, compiled languages. And then very excitingly, interpreted languages. This is really cool, and I will not go down this rabbit hole for this talk, but how they have dwarf stack frame unwinding as part of that is pretty cool. So that's all the background on continuous profiling of the stuff that you need there. Really, all you need to know is that it gives us high performance, language agnostic CPU profiles in this case. So, you still with me? Good? Cool? Great, all right. Concept number 2, reachability analysis, right? So the academic definition is it's a method used to determine whether a particular state or condition in a system is reached from a given initial state. That's a bit too academic for me. I like referring to it as a library. So imagine you want to give access to your child to a book, but there's swear words in books in the library somewhere. You obviously don't want your child to read those bad words. So instead of saying, hey, I'm just going to block you from the whole library, you actually go to the shelf, get the book, read the chapter, the page, the sentence. Does that sentence actually contain the swear word? No. Okay, fine, your child can read the sentence, that's fine. Oh, it does, hey, maybe you don't read that page, instead of just throwing out the whole library. So actually drilling into whether it's reachable or not is the best metaphor I've heard for reachability analysis. Now, tooling around this, SAST is a very popular tool around this. There's a couple other ones I'll mention on other slides. But they just make it really easy in YAML that you write the rules around what's reachable, right? So exec in this particular case is a bad JavaScript pattern. We don't want to allow that in our code base. Let's write a SAST rule to block that. Great. Now, I was a little unfair when I said that vuln management is broken. We can probably drill into this in a bit more detail of exactly the level of this. And so at the base level manifest analysis, right, it just looks at, what are the packages pulled in. That's throwing out the library, right? That's not useful, right? Where it just looks at the manifest file and any open source, just the library by name, throw it out, right? Log file analysis is an incremental step on top of that, where it's the name of the package and the version. And that's better because, hey, maybe there's a CVE for that particular version, and we don't, if you've got a patch version, you're fine, but it's still too noisy, right? It was log file analysis that was pulling up the 30,000 before. Static analysis is where that same level comes in, reachability to actually do that. You look at the code base and you do that walk through the library. But it's not quite far enough towards dynamic analysis, right? Where you actually look at the application during runtime, capture real data on this dependencies interaction to give that most precise insights, right? So in this level, right, so number 1, way too damn noisy, level 2, also over 9,000. Level 3 is kind of where the best-in-class tooling is today, right? SEMGREP, CodeQL, OWASP, depth scan, a few different options there. But it really only gives you a Boolean thumbs up, thumbs down. Is this thing reachable or not? What if there was a better option? Cool. So yeah, it helps us with improving the signal to noise of the over 9000 problem, but it's still limited by static analysis and that Boolean approach. So, sorry if we can get to the new stuff early. What if 1 plus 2? Haha! Look, now I'm no mathologist, but if we had an actual way that we could sample the running performance of applications to determine whether or not, how frequently that code path shows up, with the knowledge of knowing whether or not that vulnerability is reachable, that's a percentage. That's a likelihood. We could put a number on that value. That would be runtime reachability, right? So how can we achieve that? So in simple terms, this flame graph, right? You can just look at like this one that's all the way up here. That's less likely than something that's triggered a lot more of the time, right? In a simplified version, right? So here's a couple of things, right? The common cheap thing that doesn't have a longer sleep, or the rare expensive thing. The analogy I like using here is like, imagine this is a, you go to the webpage and every single request, there's a param there that's like hackable equals false, and every single user hits that. It's a matter of time before someone looks at that and goes, hackable equals true. Versus something in a weird off exception handler that's never triggered 0.0001% of the time. That's less likely than something that's really, really visible and is actually triggered all the time. And also with the benefit of reachability analysis, the stuff that's not vulnerable, we don't have to care about that, right? We're only caring about things that are confirmed to be vulnerable. And there's a pprof link to some actual samples that we've put up. pprof is from Parker. It's a good visualization tool, check it out. And so here's the actual samples that we ran, right? So, in this case, we can see, 94.8% of the time versus 0.07% of the time, right? Of those two, assuming equal levels of criticality of the vulnerability, of those two, which one would you patch first, right? The 94%, right? It just seems intuitive to me, but this is what I want your feedback, like, come heckle me afterwards, tell me why I'm wrong, please, but this seems like a logical way that we should be trying to prioritize vulnerabilities. Now, the obvious question for those that might be jumping ahead is, where do we get this simple information from, right? Because you need to know what the vulnerable code path is, right? Well, thankfully, some ecosystems do this. Thank you, Go. Go gives vulnerable simple information. Right there, and so you can say, for this particular vulnerability, which maps to a CVE, this is the specific function, right? It's not exploitability, right? It doesn't say, hey, here's the payload that you need to go in there, but you can at least go, look at that, map it to a profile, and say, if that name is the same as the other one, cool, that's reachable enough. But how do we do this for other ecosystems? This is the fun challenge. So, OSV is a data structure for open source vulnerabilities. It contains this information because there's Go vulns, there's GitHub security advisories, there's CVEs. This is just a way that they all get aggregated into a JSON data structure. Excuse me, that is easily wrangleable, and they have a field across all the different languages. They have the field for symbols within Go. And it looks like this, right? So in this particular case, I trimmed it a little bit with the symbol field post user login in this case. Now, the magic of AI comes in very handy at this point. So I pre-trained a specific thing with a couple of prompts, and here you're a security expert performing the task of enriching known vulnerability data from publicly available sources to assist software developers to better patch their applications. I've also found that providing evocative language, like it's really important that you do a good job, improves the accuracy of these things. I gave it that existing Go JSON structure and said, here's an example of this particular one. And then, you don't see it quite in the notes here, but in the attachments, I gave it a reference to a new CVE from Ruby, which does not provide this simple information, a link to the code base, and said, hey, read the CVE information, natural language, infer from that and the code base, populate this field for simple information, please. And it did. The accuracy is okay. It's certainly not completely automatable. You still need a human in the loop to verify these things, but it's at a point where, and definitely play around with the different models. I found complexity to be the most accurate. The information that you get out of these things is close enough where we can actually start possibly creating this for other languages, which is exciting. And yeah, here you go. So this is the ones that are created for that particular CV that previously didn't have symbol information. So now I'm getting OSV structured documents with symbol information for languages that don't provide it by default for CVEs. Right, okay. So I've got symbol information, and I've got now possibly the ability to continuously profile some stuff. Cool. Please give it a crack. So deploy Parker yourselves in clusters. So Parker is very easy to deploy within Kubernetes. They've got a bunch of Helm charts and stuff that you can deploy yourself. Play around with Perplexity or whichever AI system you recommend. And there's OSV.dev symbol information for generating that, and then filter based off the percentage that makes sense to your organization, which got trimmed off that slide. So for me, the way that I imagine this would actually be showing out, right? So you've got something like this in your dashboard, you've got this big toggle up the front, and you go, hey, for our organization, I need to prioritize my efforts. I'm just going to start with things that are above 80% likely. And then you just filter it down, and then you have a list of more manageable things. And then once you do that first pass, okay, cool, maybe you can tackle it down, right? With infinite resources, you'd love to patch everything, but that's not reasonable. And so that's the thing that I want to call out, is that this is absolutely not saying that we shouldn't patch the things, right? If we had infinite resources, absolutely, right? It's not to say that the things that are less likely are not exploitable. They still are. You should try and patch them. However, we're all constrained in terms of our resources, and so we need a ability to determine which ones actually make sense. And so, okay, well, this one's more likely, I'm going to prioritize those ones first. That's the concept of it. By the way, I'm hiring pretty much across the board. This is kind of more of a research project, but AppSec, InfraSec, CorpSec, DNR, if you're interested in stuff, please come have a chat. That's the speed round of the talk. I believe we've got heaps of time, because I absolutely sped ran that and had way too much coffee. But hopefully that was interesting. I can hang around for Q&A afterwards. Thank you so much.
One thing I forgot to mention, it's actually Frenchie's birthday today. We should all give him a round of applause.
Thanks, buddy.
For a great talk.